Hello students, so today we are going to start unit 9 of the science class 10th textbook Samachir Kalvi, which is the Tamil Nadu government's textbook, and the chapter's name is Solutions. So effectively we are basically talking about mixtures here, about which you have already learnt in lower classes, and these are some of the topics that we will cover in this chapter. Now, without spending any more time, let's look at what we have over here. See, what do you see? See, basically we have got a solution, right? In daily language we call this solution. So this is basically solid in liquid, salt in water, and next sand in water. Again, in daily language we call this, hey, sand in water sort of solution. But scientifically you have to be very careful when you use the word solutions, right? And we will talk about it in this chapter. So don't just say anything as solutions, because scientifically it's different. Good. Now another important thing to note is that if the amount of salt is small and if you stir the water after putting in the salt, then you do know that the salt disappears, whereas the sand will never disappear. Now these are some of the observations that you already know, you are aware of. Now with this in mind, let's start our chapter on mixtures. Well, you see, as I have already told you, this is again a mixture, salt in water. Now the substances present in the mixture may be present in one or more physical states, right? So these are two examples. Let's have some more example. You see, when we burn wood, the smoke released is a mixture of, you see, carbon dioxide, carbon monoxide, but in elemental form these are just two compounds of carbon and oxygen. Now, you see, in some cases of mixtures, the components can be separated easily, either by physical or chemical methods, whereas in some other cases they cannot be. Okay. Now, let us consider two mixtures, one which contains salt and water and the other which contains sand and water. So these are the examples. Now you see, water is one of the components in both the mixtures, whereas you see in this first case salt dissolves in water whereas sand doesn't dissolve. Now sand in water can be separated by filtration process, you see, but salt cannot be separated as it dissolves in water to form a homogeneous mixture, and it is this homogeneous mixture which we scientifically term as solutions. So what are solutions? Scientifically, they are homogeneous mixtures. What do you mean by homogeneous mixtures? So let me spend some time on it. So basically what is happening is that, suppose there are molecules of water over here, right? And then we have also got the salt molecules. Suppose these are the salt molecules. Now homogeneous means they are evenly spaced. Everywhere you will see they are evenly spaced. Now instead of this, what we see in the case of salt is something different. In the case of, so this is basically your this is your salt molecule and this is your water molecule, right? And this is a homogeneous mixture. Now in the case of a heterogeneous mixture like this, so this is effectively your salt water and this one is your heterogeneous mixture. What you will see is something different. Say for example, see, all the sand is at the bottom, whereas the water over here, there's some at the top, some of the sand, but mainly water is at the top. So in the case of heterogeneous mixture, something like this happens. is that the water molecules are at the top, whereas the sand particle or sand molecules are at the bottom. So you see they are not evenly spaced or evenly distributed, right? Whereas here they are both evenly distributed. So this is why we call this heterogeneous solution and this one homogeneous solution. Okay, students? So basic idea, you must keep this in mind. Now, so are these the only examples in daily life? Of course not. You see, we often encounter solutions in our daily life. You see, one of the naturally existing solutions is seawater. Now, we cannot imagine life on earth without seawater. You do know, right, that seawater is effectively, so what's seawater? Seawater is effectively water plus lots of salt, lots of various salts together. And where do we get the salt? You see, when the earth was being formation, there were so many volcanic eruptions going on, and as a result of it, both inside the sea as well as on the earth, as a result of it, many elements, many salts, many compounds, they were emitted by these volcanic eruptions and they mixed with the water. Even underground volcanoes, on earth volcanoes, all that. And basically this is the reason for the salinity of water, right? So as I was saying, it is a mixture of many dissolved salts. Now another example is air. We just can't live without it, and we do know that air is basically a mixture of gases like nitrogen, oxygen, carbon dioxide and others as well. Now let us have some more discussion on the importance of solutions. You see, all life forms on earth are associated with it. Say take another example over here. You see, plants take solution of nutrients for their growth from the soil. Okay, so if this is a plant or tree, so here basically the solution enters through the root above and it enters the different parts. So that's the idea. Now most of the liquid found in human body, including our blood, lymph and urine, they are all solutions. Now day-to-day human activities like washing, cooking, cleaning and few other activities, they also involve the formation of solution in water. So note that most of the solutions that we work out with are involving water. Now similarly, the drinks, what we take like fruit juice, aerated drinks, tea, coffee, etc., they are also solutions. Therefore, the ability of the water to form solutions is responsible for sustenance of life. Okay, so now let us talk about the components of solution. So we just learned that a solution is a homogeneous mixture of two or more substances. Now you see, so if two or more substances, then there will be scenario when one of the substance is in large amount and another two or more substances are in small amount. Okay, so you see, in a solution the component which is present in lesser amount, and when I say lesser amount, it's not by volume, this is by weight. So suppose we have a two component solution, right? Two components, only two components are here. So this is a two component solution, and here this is the amount which is lesser, and this is known as your solute, and the one which is present in larger amount, again by weight, it is known as solvent. So just right now when we talked about salt water, you do know what is salt then? Well, salt is effectively the solute and water was the solvent. Okay, so as I was saying, you see the solute gets distributed uniformly throughout the solvent and thus forming the mixture homogeneous. Now see, for example, over here, this is what you can understand very nicely from this figure. You see, the solute gets evenly distributed, right? So the solvent acts as a dissolving medium, and this process of uniform distribution of solute into solvent is known as dissolution. Okay. Now something must be, you must be thinking something. Let me help you with it. So for example, look over here. What is this? This is solvent. Good. So this is solvent, say for example water. So basically we have got water molecules everywhere. It is not shown in the figure over here. Right. Good. Now when the solute falls in water, where does it go? We do know that in the case of sand, they just go into the bottom. But if this is a true solution or just a solution, what happens is that this particle, so suppose this is one of the solute molecules. Solute molecule. So what happens is that this, after you stir it, the solute molecules enter the gap between the water molecules. You see there is lot of gap between the water molecules, and the solute particles enter into these gaps, and as a result we get an even distribution of water molecules and solute particles. Okay, so keep this in mind, dear students. Now what do you think about it? All solutions are mixtures, of course. What is a mixture? When we mix something, right? Now mixtures can be uniformly distributed or homogeneous, right? Or they can be non-uniformly distributed or heterogeneous. And right now we are talking about homogeneous mixtures, which are basically solutions, right? So all the solutions, they are effectively mixtures. But see, there are some other mixtures which are effectively heterogeneous solutions, right? So this means all mixtures are not solutions, but all solutions are mixtures. Now you see, as I was saying, a solution must be at least consisting of two components, a solute and a solvent. Now, such solutions which are made up of only one solute and one solvent, so basically only two components, they are known as binary solution. Say for example, let me show you example. Yes, over here. See, what do you see over here? This is basically a copper sulfate. This is how it looks like. So you add copper sulfate in small amount in water, and as a result you get this copper sulfate solution. Okay, solution of copper sulfate in water. See the color, it's somewhat bluish, right? And most importantly, it is uniformly colored. Just let me zoom it a little bit more. See the color of the solution itself, it's uniformly distributed. It's not that it is darker over here, it is lighter. No, it's more or less uniform. So this is because this is a solution, right? Okay, right. Okay, now you see this copper sulfate solution, it again contains two components. One is your copper sulfate and another, so solute is your copper sulfate and the solvent is your water. Now similarly, a solution may contain more than two components. So as I was previously showing you, for example, if salt and sugar both are added together in water, and then both will dissolve in water, forming a solution. So what will happen in this case? In the case of a salt sugar solution, so if these are water molecules, so suppose these are water molecules, right? Water molecule. Molecule, and let me use different color, and these are salt molecules, so they go in between. So these are salt molecules. And next, let me use a different color, and these are your sugar molecules. So you see, they are both entering the gaps. More or less, they are evenly distributed. See? So these are basically your sugar molecules. So this is what is happening. Now in this case, how many solutes we have here? We have got two solutes, salt and sugar, and the solvent is water itself, right? So basically we have got a situation of two solutes dissolving in one solvent, and this type of solution which contain three components, they are basically known as ternary solutions. So keep this in mind, dear students. Okay, now let us talk about types of solutions. Well, we do know that substances exist normally in three physical states or phases, which are solid, liquid and gas. Of course, there is the fourth phase of matter, which is known as plasma. Fourth phase or state, which is plasma. It is not easily observed. Basically, one of the examples is lightning that you see during thunderstorms. Okay, now, but you must remember that this is yet another state. Actually, there are even more states, but right now let's concentrate on only solid, liquid and gas. Now in the case of binary solutions, both the solvent and solute may exist in any one of the physical states, right? So we have solute and we have solvent. Okay, so see, solute can be solid, liquid, gas. Again, solvent can be solid, liquid, gas. So overall 3 into 3, right? So many possibilities are there. Now, you see, but the solvent constitutes the major part of the solution. Its physical state is the primary factor which determines the characteristics of the solution. So basically, the solvent's properties dominate the properties of the solution. Therefore, we can have, you see, the following types of solutions. Here we have some examples. Say for example, solid in solid. Say copper dissolved in gold. So solid in solid example is alloy. So what's an alloy? Alloy is basically a homogeneous mixture or a solution. So example, copper dissolved in gold. Next, liquid in solid. Say for example, mercury in solid, which is also known as amalgam. Next, liquid solutions. So solid in liquid, say sodium chloride dissolved in water or salt dissolved in water. Next, liquid in liquid. Say for example, ethyl alcohol dissolved in water. What do you think if you dissolve milk in water or your ink in water? Will you get a solution? Actually, it's not a solution. It's a heterogeneous mixture. Okay, and we will talk about it later on. Next, gas in liquid, say carbon dioxide dissolved in water, soda water, and you must know that all the aquatic animals and aquatic plants, the reason they are alive is because there is water, there is oxygen and carbon dioxide dissolved in water, and that's how inside water they can inhale or they can undergo the process of respiration, sort of. They need oxygen and carbon dioxide, and this is how they get since these gases are dissolved in water. Next, gaseous solutions. Liquid in gas, say water vapor in air. Of course you do see clouds. What is it? It's basically mixture of water vapor in air. Next, gas in gas. So mixture of say helium, oxygen gases and so on. Or our air. Air is basically mixture of several gases here. Now you see, we can also distinguish solution on the type of solvent. You see, most of the substances are soluble in water. That's why water is called universal solvent. However, you see, some substances do not dissolve in water. Therefore, other solvents such as ether, benzene, alcohol are used to prepare solution. On the basis of type of solvent, solutions are classified into two types. So first is the aqueous solution, where the water acts as solvent, right? Say for example, common salt in water, sugar in water, copper sulfate in water. And another is non-aqueous solution. That is a solution where any other liquid other than water acts as solvent. Okay? So, examples, we have alcohol, benzene, ether, carbon disulfate, acetone. They are being used as solvents. So, they are basically non-aqueous solvents. So, some examples of non-aqueous solutions: sulfur dissolved in carbon disulfide, iodine dissolved in carbon tetrachloride. See, this is sulfur in CS2, and again remember this is water, and see, if you put in the sulfur, it just settles down at the bottom. Why? Because it is insoluble in water. However, it is soluble in CS2. See? Now, based on the amount of solute, we can also distinguish solutions. You see, the amount of solute that can be dissolved in a given amount of solvent is limited under any conditions. Why? Why does this happen? Just think about it. If these are solvent molecules, right? Suppose these are solvent molecules, okay? So what's the problem? The problem is that the solute molecules do have fixed space. They are basically entering the gaps. Now once all the gaps are filled up, then the solute cannot enter. And then what will happen? The solute will just float around on the top, or they will sink at the bottom. So this is what is going to happen, right? And this will happen once all the gap is filled up. And this gap effectively depends on temperature and pressure. So for example, if I increase the temperature, what will happen is that the solvent molecules, they will gain kinetic energy, right, due to heat, and they will move apart from each other. So their gaps will increase, and as a result now more number of solute molecules can enter. Now if we cool down the temperature, then their kinetic energy will decrease, and effectively their gaps will decrease. So you see smaller number of solute particles. So increased temperature and large number of solute molecules can enter gap between solvent molecules, right? However, you see lower temperature, lower volume of gap between solvent molecules, and so less number of solute molecules in the gap. So if there is 3 solute molecules, there can be much more, you see, in this gap over here. So this is just an example. I am basically effectively explaining this concept of saturation, unsaturation, molecular theory. Okay. So based on the amount of solute in the given amount of solvent, solutions are classified into the following types: saturated, unsaturated, and supersaturated. So what saturated solution? You see, a solution in which no more solute can be dissolved. So the situation like this, no more solute can be dissolved at a temperature, is called saturated solution. Example, 36 gram of sodium chloride in 100 gram of water. You have to mention the temperature as well. And the temperature is 25 degrees centigrade. And this forms a saturated solution. So if you try to dissolve 35 gram of sodium chloride, then it will be dissolved. At that time, you will not call it saturated solution. But if you want to dissolve, say 37 gram of sodium chloride, then you will observe salt at the bottom of the solution, because then all the gap is filled up. Okay. So next is the unsaturated solution. Well, unsaturated solution is one that contains less solute than that of the saturated solution at a given temperature. So see, if I try to dissolve this 35 grams of sodium chloride in 100 gram of water at 25 degree, then what I will get is basically an unsaturated solution of sodium chloride in water. Okay, so keep this in mind. Next we have got supersaturated solution. That is one which contains more solute than the saturated solution. So here the example is 37 gram. If I try to dissolve in water, then this is basically your supersaturated solution. Again you have to mention of sodium chloride in water, and you have to mention the temperature as well at 25 degrees centigrade and at again 25 degrees centigrade. Now let me ask you, my dear students, suppose I increase the temperature to 65 degrees centigrade, what will happen? Then you will see that this is already unsaturated, no question about it. This will remain unsaturated, but the solvent molecules or the water molecules, the gap will increase, and probably this 36 plus 1, this 1 extra gram which is not being dissolved, now it will be able to enter the gap, and as a result this time we might have a situation where you will see that this has also become an unsaturated solution. Okay, you will see that probably at 65 degrees centigrade 45 grams of sodium chloride at 100 degree at 100 grams of water will be effectively at 65 degrees centigrade is now your saturated solution. So you understand what I am saying? If I change the temperature, the amount of solute changes. So at 65 degrees centigrade and at for 100 grams of water, 45 gram is needed to make it a saturated solution. So keep this in mind. Now you see this supersaturated solution, this state can be achieved by altering any other conditions like temperature, pressure. Supersaturated solutions are unstable and the solute is reappearing at crystals when the solution is disturbed. When I say disturb, I mean change in temperature, change in pressure, something like this. Okay. Now you are given two samples of solutions of sodium chloride. Can you identify which one is saturated? Of course, if I keep on adding a little bit more amount of salt in it, the solution where the salt will be seen at the bottom, then I will say that previously that was my saturated solution. And the other case where the salt will get dissolved after stirring the spoon, then I will say previously this was an unsaturated solution. Okay, you see the next concept is that of concentrated and dilute solutions. Yet, this is yet another way of classification of the unsaturated solutions. Remember this. Now basically what we are going to do is we are trying to express the relative concentration of two solutions with respect to their solutes present in the given amount of solvent. So for example, let me give you a daily life real example. You are given 2 cups of tea. When you taste them, you feel that one of them is sweeter than the other. What do you infer? Basically, the tea which is sweeter, basically it contains higher amount of sugar than the other one, right? Now how can you express your observation? You can say that the tea is stronger, but a chemist would say that it is sort of concentrated. That means when you compare two solutions having same solute and solvent, then the one which contains higher amount of solute as per the given amount of solvent is known as concentrated solution. And the other one where the solute amount is lesser, it is known as dilute solution. See, we are showing this in the diagram over here. You see? So basically this is your solution, this is the solvent, and these are solute particles, right? See, these are the solvent over here, and these are the solute particles or solute molecules. How many molecules do you see over here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just representative. Don't think this is actual. Actually, it is of the order of 10 to the power 23 to 10 to the power 22. Okay, don't think about it right now. It's much, but just representative. You see, there are smaller number of solute molecules, and here we have much more number of solute particles or molecules. Okay, so you see, differentiating solutions as dilute and concentrated is effectively a qualitative representation. It does not imply the quantity of the solute. This difference is observed by means of some physical characteristics such as color, density. Of course, the density is much more over here, higher density, right? Higher density, and because of this more number of solute particles, the color can change as well. Color is different compared to the color over here, and here again the density is higher compared to here, because in a unit volume, you see, there are more, say if I consider this space as the unit of volume, here there are solvent plus say 2 solute particles, whereas if I consider the same volume over here, then here we have got only one. Overall, I am just saying. So you can just say that here the density is higher since the number of solute particles is higher. Next, just look at the color and of these two pictures. So this is T, 2 varieties, again copper sulfate, 2 varieties. So can you say which one is dilute and which one is concentrated? First, this one, you see the color, it's very light, and this one is deep. This means there is much more copper sulfate in water. So of course, this is the concentrated solution, and this one is your dilute solution, right? Now in this case, again the T color is much more light over here. So this is my dilute solution, and the one which is darker means there is much more T particles in water over here. So this is my concentrated solution. Okay, students. Now we will talk about solubility. Previously, you do remember I showed you using this diagram that there is a limit to the amount of solute that can be dissolved in a given amount of solvent at a given temperature. This has to do with the gaps, and we discussed this using the salt and sugar as solvent in water, and the temperature is, say for example, 25 degrees centigrade, right? Say for example. Okay, now when this limit is reached, we have got a saturated solution, and any excess solute that is added simply settle down to the bottom of the solution. The extent of dissolution of solute in a solvent can be better explained by its solubility. Now we have to quantify the things. When I say that if I add something, it just goes down at the bottom, that's it. So this is a qualitative statement. Now as scientists, as a student of science, you have to learn how to quantify a thing. And so we are going to learn the concept of solubility to quantify, okay, this thing. So effectively, solubility is a measure of how much of a solute can be dissolved in a specified amount of solvent. Now, effectively, we can define solubility as the number of grams of solute that is dissolved in 100 grams of a solvent to form its saturated solution at a given temperature and pressure. Let us take some examples. Say 36 grams of sodium chloride need to be dissolved in 100 grams of water to form its saturated solution at 25 degrees centigrade. So what does this mean? This means that the solubility of sodium chloride in water is 36 degrees centigrade, and you must always mention the temperature, that is at 25 degrees centigrade, right? So it's 36 grams at 25 degrees centigrade. Now this solubility is mathematically expressed as mass of solute by mass of solvent into 100. So suppose I ask you, hey, I have got say 43 grams of sodium chloride, right? And I am dissolving it in say 121 grams of water. So can you say if this is a saturated or unsaturated or a supersaturated solution? So if such a scenario happens, then this concept becomes important. See, let me show you through example. So here what we have learned is that using this concept, if I use this, so effectively my solubility is equal to mass of the solute, which is 36 grams divided by your 100 grams of water, 100 gram. So this is how much? Gram will cut down into 100. So effectively 100 cuts down. So this is 36%. Right? So effectively. Or you don't have to say just percent, you just say 36. So effectively this is your 36. Next, let us try to compute for this. So effectively this is 43 grams by 121 grams into 100. So this one, if you work it out, so this is effectively 35.54. Now see, this amount is lower than 36. So you can say that this solution is basically an unsaturated solution. See, you understand the concept? So we do need this important definition of solubility, right? Now here you can see the solubility of some common substances in water at 25 degrees centigrade. So solubility in gram by 100 grams of water. So calcium carbonate is very less amount. Sodium chloride is high. Ammonia is high. You see sodium hydroxide is again very high. Glucose is also high. Sodium bromide is high. Now sodium iodide is really high. Okay, see, in 100 grams, 184 grams of water can be dissolved. So this is the first case where effectively amount is even more than that of water. Okay, and this one is 95 grams, so effectively 50-50 you can say for sodium bromide. Now let us talk about some of the factors which affect solubility. Effectively there are three main factors. First is the nature of solute and solvent, then temperature and pressure. You see, the nature of solute and solvent plays an important role. Although water dissolves an enormous variety of substances, what are ionic and covalent, we do know about it, right? It does not dissolve everything, and the phrase that scientists often use when predicting solubility is like dissolves like. What does this mean? This just means that basically it means that dissolving occurs when similarities exist between the solvent and the solute. For example, common salt is a polar compound and it dissolves rapidly in polar solvent like water. Now, you see, non-polar compounds are soluble in non-polar solvents. So, for example, fat dissolves in ether, but non-polar compounds do not dissolve in polar solvents, and polar compounds do not dissolve in non-polar solvents. So, polar solvent, so polar, you see what I am saying over here, polar compounds. Polar compounds, they dissolve in polar solvents, and non-polar compounds, they dissolve in non-polar solvents. And the other one is just not happening. So polar compounds will not dissolve in non-polar, and non-polar will not dissolve in polar solvent. So see, fat does not dissolve in water, since fat is non-polar compound and water is a polar solvent. Okay, good. Now let us talk about effect of temperature. You see, Solubility of solid in liquid. You see, generally solubility of a solid solute in liquid solvent increases with increase in temperature. I have told you the reason, right? Increasing in temperature means increasing the kinetic energy of solvent molecules. They go far apart a little bit, so the gap between the solvent molecules increases, and then more and more solute particles can enter the gap in between. So that's the reason why a greater amount of sugar will dissolve in warm water than in cold water. Now, in endothermic process, solubility increase with increasing temperature, and in exothermic process, solubility decrease with increasing temperature. You see, what's an endothermic process? An endothermic process is basically a chemical or physical process where heat is absorbed from the surrounding, and this absorbed heat is transferred to the system, and so the system, basically the solution's temperature increases. Since the temperature increases, so the gap of the solvent molecules increases, and that's why the solubility increases. Whereas in an exothermic process, what happens is that heat is released from the system, and this heat comes from the system itself. So since heat is released, the entire solution gets cooled colder. So this means the temperature of the entire solution, it decreases, and as a result the gap between the solvent molecules decreases, and so now the solubility decreases, since there can be less number of solute molecules which are able to fit into the gap between the solvent molecules, right? Next, let us talk about solubility of gases in liquids. Do you know why is it bubbling when water is boiled? You see, solubility of gas in liquid decreases with increase in temperature. Generally, water contains dissolved oxygen, and when water is heated, the solubility of oxygen in water decreases. So oxygen escapes in the form of bubbles. Why do you think this is happening, my dear students? See, this is liquid, okay? Yes, this is liquid. Effectively, this is liquid molecules, and there is, say for example, let me just first write it down, and then there is your gas. These are gas molecules dissolved in it. Now, when I boil water, say for example, so what happens is that oxygen is dissolved in water, right? Now you see, because of this heat, the oxygen molecules, they get energy, right, from this heat, and now since they get more and more heat, so their kinetic energy increases, and see, they are gas, so as a result they just escape the system, and this is the reason for the bubbling phenomena when water boils. Okay, good. Now aquatic animals, they live more in cold regions because more amount of dissolved oxygen is present in water of cold regions. This shows that solubility of oxygen in water is more at lower temperature, because at that time more and more oxygen atoms can be dissolved in water, and they will not escape normally the gap because their energy is also low. So if you heat it, their kinetic energy increases, and then they just break the bonds or whatever in this water, and then they will just escape the water. Okay. Now, effect of pressure. You see, effect of pressure is observed only in case of solubility of gas in liquid. When the pressure is increased, the solubility of gas in liquid increases. Effectively, pressure means I am pushing in from all directions. So liquid, they cannot be compressed, but gas can be compressed, and so if I push in from all sides, where will the pushed gas go? it will go inside the liquid, and so the solubility increase of gas in liquid increases if the pressure is increased. Okay, so some common examples of solubility of gases in liquids are carbonated beverages like soft drinks, household cleaners which contain aqueous solutions of ammonia, formalin aqueous solutions of formaldehyde, right? See, effect of pressure and solubility. Look into this figure, you will be able to understand. So if P1 is the pressure and P1 is yet another pressure, now see P2, P1 is the first pressure, P2 is second pressure. Now this is much more, right? This pressure is much more than this P1. So if I keep on pushing this, where will this gas go? It will just enter the liquid. So this is basically increasing the presence of gas inside the liquid. See over here, this is carbon dioxide inside your cold drinks bottle. This is a 2-liter cold drinks bottle. Now if you just little bit shake and then open the cap, then what will happen? Bubbles of carbon dioxide will form, and then they will just leave, and some liquid is also goes out, and you will see a foam at the mouth. So this is what happens. You see, the effect of pressure on the solubility of gas in liquid is given by Henry's law. And what does this Henry's law state? It states that the solubility of gas in liquid is directly proportional to the pressure of the gas over the solution at a definite temperature. So this is important, students.